Assalamualaikum and greetings to Dr. Siti Hajar. My name is Fatih Zahra binti Rosihan from Group A4. We will present to you about the stretchable conductive ink with new formulations. These are my group members.
My name is Nurfahana binti Muhammad Yusuf.
My name is Nur Umairah binti Nuri.
My name is Nur Farisha Shamil binti Muhammad Fazil.
My name is Nur Sadida binti Abdul Rashid.
My name is Muhammad Azizan bin Mustafa.
To summarize all, the project are conducted to choose a newly formulated SCI material that can be developed into a highly conductive, stretchable and reliable at varying strain and temperature on flexible PCB board. The reason is because the existing material used in inflexible PCB board has limitation to be used on flexible PCB board. After considering a few factors, we have chosen poly-3,4-ethylene dioxythiophene polystyrene sulfonate as matrix material, graphene as metallic fillers, and thermoplastic polyurethane as substrate material for the new SCI material formula. The presentation will explain all the functional requirements of each material.
The problem statement is the limitation of conventional interconnect materials such as in soldering process. Improper solder on PCB between the components during the soldering process can cause a lifted pad of component lifting from PCB and ruin the board. It also can affect the component to a short circuit and burn up.
Printed circuit board, known as function to mechanically support and electrically connect electric components using conductive pathway, threads or signal traces etched from copper sheets laminated onto a non-conductive substrate. PCB are often a flat laminated composite comprised of non-conductive substrate materials with copper security concealed internally or on the external surface. It has a laminated sandwich structure of conductive and insulting layers. The layers of two complementary functions are to affix electronic component in designated location on the outer layers by means of soldering. Electric components are mounted on the board and connect all the components together to form a working circuit. Next, conductive ink is a type of ink that can conduct electricity as the name suggests. To enable electrical conductions, most inks are impregnated with a conductive substance such as graphite or silver. Printed circuits, organic light emitting diodes, radio frequency identification tanks, and battery test stripes are all made with conductive ink in the printed electronics industry. In addition, the stretchable conductive ink is a useful substance that improves the electrical conductivity of the ink layers after stretching and folding. It has a wide range of potential applications in the realm of flexible electronics devices. While maintaining the electrical and mechanical integrity, the SCI are able to stretch by at least 500 cycles without increasing its resistance by more than 30 times of the original resistance.
Next, let me explain about the definition and application of nanocomposite. Nanocomposite can be defined as a composite with nanoscale morphologies such as nanoparticles, nanotubes, or lamellar nanostructure in one phase. It also can be defined as a matrix to which nanoparticles have been added to improve a property of the material. For the application, the first one is making composite with even greater strength to weight ratio using graphene. The researchers discovered that by adding graphene to epoxy composites makes them stronger and more stable. The second one is speeding up the healing process for broken bones. The researchers discovered that by using a nanotube polymer nanocomposite as a scaffold to guide replacement bone formation, the replacement bone growth is accelerated. Lastly is making lightweight sensor with nanocomposite. Patches of polymer nanotube nanocomposite can be used as stress sensor on windmill blade because of this feature.
In this section, there will be three formulations of materials. First one is poly-3,4-ethylene dioxythiophene, known as PEDOT PSS, and the second one is the thermoplastic polyurethane, known as TPU, and the last one is the graphene. PEDOT PSS is made up of negatively charged saturated PSS and positively charged conjugated PEDOT. By applying various solution processing technique, its aqueous dispersion can be treated to produce a thin film on a rigid or flexible substrate. Thus, it can produce a smooth and excellent film for use as electrodes in electronics. PEDOT PSS is one of the best choice for flexible electrodes. It is due to the high transmittance in the visible range, high and adjustable conductivity. It also excellent in thermal stability and good film forming capability as well as superior mechanical flexibility. TPU is important class for thermoplastic and thermosetting polymer due to its mechanical, thermal, chemical and adhesive properties, which can be defined to a proper combination of a huge variety of polyols and isocyanates of building blocks. This TPU is a product of polyaddition reaction between three components, which is diisocyanate, long-chain diols, and also short-chain diols. The flexible polyurethane segment is made up of long-chain diols, whereas the rigid polyurethane segment is made up of diisocyanate and also short-chain diols.
Formulation of graphene. First, graphene is made up of only one atomic layer of carbon atoms, which add to its super thin and lightweight properties. Second, the unit structure of graphene is hexagonal carbon ring, with an area of 0.052 nanometer square. Third, because each atom at the vertex is shared by 3 unit rings, such a ring only has 2 carbon atoms.
There are 7 processing techniques. First, the design is created. Second, the screen is prepared. Third, the emulsion is exposed. Fourth, the emulsion is washed off, creating the stencil. 5. The item is prepared for printing. 6. The ink is passed through the screen onto the item. 7. The product is dry, checked, and finished. Testing procedure. For the first step, to make the conductive ink, 0.7 gram GNP were combined with 1.3 gram BPAXOZ and 0.39 gram theta hardener. Second, the gross weight of the binder was determined using the analytical balance. Third, the beaker was placed in the baking pan center and the door was closed. Fourth, for the few seconds it was left behind to allow the unit to stabilize. Next, test pattern was created in 4 different designs, which is straight line pattern, curve pattern, square pattern, and lastly zigzag pattern. 6. Cutting the TPU substrate. 7. Attach the TPU to the back of the screen using cellophane tape. 8. The conductive ink were then sprayed on the back of the screen after the TPU was removed from the screen. 10. The curing process took done in the universal oven UF55 at 100 degrees Celsius for 30 minutes. 11. The printer sample placed on the tray can be placed in the oven dryer directly after the printing process is completed by preheating the oven. Lastly, step is, after the printing sample had been cured, it was allowed to dry completely at room temperature. The samples were ready for analysis after the curing process.
Next, let's move to the theoretical formulation for the fabrication of conducting ink. The first one, conductive ink was prepared by mixture of graphene solution as a filler and P.PSS as a binder agent. Second one, 10 mg of graphene nanopowder was mixed in 5 ml dimethyl sulfoxide DMSO solution to make graphene solution. Then, the solution needs to be sonicated by prop sonicate for 30 minutes and stirred at room temperature for 24 hours. The next step is, the screen for screen printing were masked with an array of 42 rectangular tracks, which is 2 times 30 mm. Graphene ink was printed by using 77 threads per cm and 100 threads per cm for P.PSS on stretchable conductor, which in this project we chose TPU as our substrate. Lastly, to finish the polymerization, the screen printed fabric with GMP fill ink was baked in the oven at 150 degrees Celsius for 3 minutes.
This material is needed to perform electrical tests and to evaluate the influence of the amount of graphene on the effective electrical conductivity of field paint. 5 films of inks loaded at 2, 2.5, 3, 3.5 and 4% of graphene were generated on a cutting-coated mylar substrate. Next, between the 2 opposite connections of each specimen, measurements of voltage were taken. Therefore, the effective electrical conductivity was calculated from the measured resistance values, considering the size and thickness of the manufactured specimens. Stretchable silver-based inks, SCI, were one of the many materials used in stretchable electronics projects. The electrical performance was limited to a maximum of 10,000 bending cycles or until the conductor snapped. It takes roughly 10 seconds to complete a bending cycle. During the bending mechanism, the resistance values were recorded at 1000 cycle intervals. The initial shear resistivity of SCI is less than 30 meter ohm per square or 25 micron. The figures show how it responds to stress in a usual way. When porous substrate absorbs the polymer, it leaves the conductive phase on the substrate, which caused the lowering of the resistance. The resistance also influenced by the composition of the cured inks. Resistance is affected by the number, shape, and orientation of silver particles, particle size, distribution, polymer amount, and additives. The screen printing technology was used to create electrically conductive patterns of flexible PCB materials. As a conductive medium, silver ink was used. The electrical and mechanical properties of silver ink conductors are influenced by the composition and amount of polymer matrix, as well as the particles' size, amount, shape, distribution, and orientation.
Conclusion is the electrical conductivity of composite can be increased and enhanced by adding conductive filler to the matrix, such as carbon-based materials. As the filler content in the composite increase, the conductive filler particles start to contact each other. Conductive polymer composite have a higher electrical conductivity and superior mechanical characteristic. More study is being done to see if adding graphene to a epoxy matrix can improve the electrical, mechanical, and thermal properties of the material. Recent advances in stretchable conductive ink technology or carbon nanomaterial offer numerous possibilities for printed and flexible electronics. Due to its promising and extraordinary properties, graphene has been widely used in the fabrication of printed electronics. Many applications in graphene-based flexible electronics will require further development of particle graphene inks, as well as improvement to a simple and efficient deposition procedure. As a result, combining novel conductive inks with efficient printing technique is expected to be a key strategy for developing the next generation of electronic device.